So today we're going to talk about zkTLS. You might have heard that as zk oracles or HTTP-Z or MPC TLS. What was the other one? I thought there was another one. But anyway, a bunch of different kind of names. I like zkTLS better, so I'm going to use that, but different projects might use different names. I kind of want to... So that's going to be my way of introducing it, but it's quite a big design space with different projects are doing different things. We have one of them today here, Hirsch from Opacity, so he can tell you more about his design decisions, but it's kind of complicated to get around that, and hopefully I'm going to do a good job to try and give you my own intuition on how to think about that, and you guys can maybe think about it this way, and maybe it helps. And so maybe I'll start with public oracles. This is my outline, but I can do whatever I want. So I'll start with this one. Public oracles are basically the idea that you're on chain and you want to prove things on chain, or you want to do things on chain that are based on what is happening in the outside world. So I don't know, maybe I can illustrate that. This is your blockchain. Stuff is happening here, and usually the outside world is sort of like out of access. Like you can only do stuff based on the universe you created for your blockchain, meaning like the tokens you created and things like that. And so if you want to get access to, I don't know, the rate between USD and Euro, the exchange rate, or information about the news and stuff like that, you can't really connect to that. So basically public oracles are the solution that we found, which is to have a bunch of guys sitting outside and posting that information, for example, in a smart contract. And either we trust one of them to do it, but usually in the blockchain world, we don't want to trust one person. So that's why we have here like a network of them, and we sort of use economic security to be like, if you guys are lying, or if we detect some people are lying, then we can punish them. We can slash them, and maybe they're staking and stuff like that. So this is, if you've heard of Chainlink, this is what they do. I actually don't know too much about that field. I don't know exactly how they're securing this kind of thing or who are their competitors, but this is one example of posting public data on chain. Does that make sense? Yeah. All right, this is good, but this only works with public data, meaning like anybody can act as an oracle and retrieve that data and check that it's correct. But what about private data? So what about, I don't know, what about me? That's me, I'm a user, and I have a private connection to, I don't know, my bank, bank.com. Or, you know, maybe I connect to like facebook.com and I want to prove that I can log in with some email. I don't know, the sky's the limit. The thing I want to say here is that this is a private connection, and the data I retrieve is personal to me. It could be my credit score, it could be my balance, it could be the number of friends I have on Facebook. These kind of things that are maybe not publicly available. And so, okay, so we can't use this public oracle stuff. What can we do? The first thing we can notice is that to access these websites, today we use this protocol called TLS. I think in modern browsers, you don't really see this HTTPS thing anymore. Maybe you see like a lock, a green lock or something like that. But anyway, you're using this protocol called TLS to secure your connection with this server. Anybody knows what TLS stands for?
Transport layer security, right?
Nice. Do you know what SSL stands for?
Secure socket layer.
Secure socket layer? Actually, I don't know. I was just wondering. But yeah, it used to be SSL, so you might have heard of that. It's kind of a Frankenstein protocol that has many versions, and servers on the web have to like support all of these different versions. Today, the last version is TLS 1.3. And so you have to support versions back to like 1.2, 1.1. I guess some of them are very insecure, so you don't really want to support them. And back in my days when I started cryptography, the only interesting stuff that we could do was work on these kind of protocols, and it was quite miserable. And now we have cryptocurrencies, so I'm happy I can work on interesting things. But some people still want to be miserable, and they go back to working on these kind of protocols. Okay, so we're talking to these servers that use cryptography to protect these sessions. Does that mean we have something that we can bring to the blockchain? Do we have some sort of web proof? Turns out that no, because the way TLS works is that servers don't sign their responses. And so if servers would sign their responses, maybe you would have a way to verify that in a smart contract. But because they don't do that, we have to be more clever. Okay, so at this point, I'm going to start introducing TLS and how it works, or at least just give you some ideas. But any questions so far on the stuff I've talked about? Yeah? So no, and all right. So TLS works by basically, let's say you have, bank.com. We're going to keep our example. And that's me, I'm the user. Usually that's the client, that's the server. And when I connect to it, I send what they call a hello message or a client hello message. Client hello. And then the server answers with a server hello. It doesn't really matter. Basically, it's kind of a back and forth. And this thing here is called a handshake. Handshake. And the whole thing it's trying to do is to find a common version between the client and the server. As I said, there's different versions. And to find a common set of cryptographic algorithms that they can use to communicate. And then they will do a key exchange. That includes a key exchange, which is the part we're interested in this part. And once they do the key exchange, then they'll get some symmetric keys, and they'll use that to encrypt. Maybe I'll use a different color. They'll use that to encrypt. There's a name for that. I can't remember, the transport layer or something like that. And the reason is that symmetric encryption is faster, so they really want to get rid of any public key crypto. So key exchange, stuff like that is kind of heavy. So you do that first, you get some symmetric keys, and then you can use something like AES to encrypt communications between the server and the client. The reason why we don't have a signature is basically this. Because this part is symmetric, we only have symmetric keys. And symmetric keys mean that when I receive an encrypted message from the server, I use my key to decrypt it, but I could also use that key to encrypt it, to encrypt the message. Does that make sense what I said? So I'm going to rephrase that, but basically with the keys I have to decrypt the server messages, I can fake server messages. That's the problem. I can create messages that look like I'm the server and encrypt them with the same key they're using to encrypt. Right? Symmetric cryptography means you're using the same key to encrypt and decrypt. Yeah, does that make sense? Yeah, nodding heads, that's good. The other thing I can talk about is that when bank.com shows up, you don't necessarily want to trust that guy. That could be like some random node on the internet. So what they do is that they have a certificate, and that certificate is actually signed by, let me make some room here. That certificate is signed by some other dudes. And these dudes, there are a lot of them actually, and we call them the certificate authorities. And basically in your browser, there's a bunch of certificate authorities public keys. And when you connect to something like bank.com or google.com or whatever, they will show you a certificate of their public keys signed by one of these dudes. And so you have to think about that as a new trust assumption. That's going to happen later. We are trusting the fact that these people are acting honestly. It doesn't happen all the time. Some people misbehave. Sometimes your browser will kick some of them or will agree. Mozilla, Chrome, Safari will agree to kick some of them. We have some protocols to try and detect attacks, but it's not a perfect world. And maybe I'll give you the name. This whole thing is called the Web PKI for public key infrastructure. So that's what I talked about, and that I talked and talked. Cool. Yeah?
So, CA sign the certificates. What do you do with the certificates?
Say that again, CA signed the certificates?
Certificates, right?
Right.
What do you do with the certificates?
So certificate, you can think of it inside the certificates. You have the name of the person you're talking to, bank.com, and you have a public key. And basically, if you imagine you're talking to someone over the internet, you think they're bank.com, but they will use that certificate as proof that they are indeed bank.com because it's signed by some people that you trust, have done their due diligence, they actually checked that the correct person. And when they issued that certificate, they were sure that these people were bank.com. Oh. Yeah. Any other questions? All right. So at this point you understand why we can just take the queries or answers, bring them on chain, right? They're not signed. I want to mention the fact that there are some RFCs, so requests for comments. These are internet standards that try to address that and try to extend TLS to have signatures of the responses and queries. But they're not really adopted. It's not clear if they will ever be. So just know that they exist. Okay, now I'm gonna get into the first solution that I'm aware of that sort of try to fix that issue. So do people know what TEEs are actually? Thank you. Trusted executed environments. Actually, I'm not even sure I remember that. You can think of like SGX or like these chips that are in your CPU or like in some server CPUs, and you can have them run some code, and you know that they'll run the code trustfully, and without you being able to see what they're doing. So I don't know how I'm gonna illustrate that, but this is a computer. there's a chip here. This is like SGX, and you're like SGX, run this thing with your maybe you have some secret keys inside of the thing, and please run this thing, and the chip will come back to you with like some results and some signature, a signature over the statement, which is I have run this program with these inputs, and this is the output. You can think of it as like a zero-knowledge proof, basically. So it's a signature that the execution ran correctly. And that signature comes from, in the case of SGX, comes from Intel. So it's kind of like a certificate authority or something like that. It's a PKI, actually. It's a public key infrastructure, where we have the public keys of Intel, and they've signed the public keys inside of that chip. It's kind of confusing, but maybe it's not very useful to know that. So this is actually a certificate chain. They signed the chip public key, and this has signed the statement. So again, you can see that as a zero-knowledge proof, but it's not a zero-knowledge proof. There's no real cryptography involved. It's like hardware cryptography. It's like we are using a bunch of techniques so that if some attackers come and look at that chip and try to like throw lasers at it or stuff like that, they won't really see what's happening. They won't be able to extract the keys. They won't be able to fake that result. Okay, that's my very short and brief introduction to TEEs. Hopefully that makes sense. But some people came up with something called town crier. I think there was another one, but this is the one I'm familiar with. And basically they said, okay, we're gonna have a smart contract on chain, and people are gonna be able to like ask town crier to make queries, and we'll make the queries inside of SGX. And since SGX has a public key, people can encrypt their queries to SGX or can encrypt some information to that chip. That chip can then, the program on that chip can decrypt it and perform a TLS query and then create this signed statement and post that back on chain. Yeah, does that make sense? I'm not too happy with that explanation, but you're trusting some hardware to do the correct thing. And because you're trusting them so much, you also trust that nobody can see what the hardware is doing. Really, you should see that hardware running on some laptop somewhere or some server somewhere as like a black box that nobody has access to. And so you can encrypt queries to it, and it will do something, and you can trust the result because it's signed.
You have to give it like your auth token, your API.
I mean, depending on the API, but it's.
Bank.com.
Oh yeah. So in this case, either you use it to query some public data, and so you trust this thing because you trust the TEE, so it queries the public data, and that's fine. Or in the case of private sessions with my cookies with my bank, then I can encrypt my cookies to this thing, and it can make the query for me. And rest assured that they're not gonna leak my cookies, so they're not gonna withdraw my money and stuff like that. But TEEs are what we call hardware cryptography, and it's not 100% sure. There's been a lot of attacks on TEEs, so usually we like TEEs, or sort of, but not to do like very, very, very sensitive things. So usually we like TEEs to like do some stuff, but we want that if they break, it doesn't completely break the protocol. It doesn't leak my tokens or stuff like that. Yeah.
Maybe quickly, as a benchmark, how using a TEE affects like speed or overhead costs, or like with metrics like that might be helpful.
Yeah. So metrics on TEEs. At this point, we didn't really have a good solution to query that data, so we're not really benchmarking that against like a baseline anyway. But TEEs are always like fast, like way faster than like cryptography, and that's why people like to use these kind of things. And that's why it's kind of hard to compete with like. It's hard to like bring some of the FHE or zkP or MPC stuff to people that need it, because they're gonna ask you like, oh, why not just use a TEE? It's much faster, and this is fine in my trust model and these kind of things. And this is the best benchmark I can give you. I'm not gonna give you numbers because I don't know. I just know it's fast. Cool. Okay. So this is not the most interesting solution. I don't know if people still use things like that today. So now I'm going to talk about the zkTLS stuff. But any question on that before I jump to the zkTLS stuff? All right. So I'm gonna keep that. All right. Up. And okay, so there's different ways to explain that, and this is kind of tricky, but the way I'm going to try to explain is that I'm going to look at the early protocol that are still being implemented. It's actually very hard to trace the history of these protocols as someone that hasn't really followed all of these things. There's different papers. People are implementing things that have the same name as the papers, but are not really doing what the papers have written. And so it's kind of confusing, but I believe one of the first paper to talk about what I'm going to talk about is called DECO. And DECO was like, we can do stuff. We have a solution with MPC, and then we have a solution that avoids MPC, which we call the proxy solution. And I'm going to start with that solution because it's simpler to explain, and some people actually use it. Some of the projects actually use it also. So the way it works is that instead of talking directly to bank.com, where am I? I'm here. I removed myself. Instead of talking directly to bank.com, I'm going to talk to a proxy. Let's call him proxy. And that proxy is going to talk to bank.com. And so when I send my handshake stuff, they're just going to proxy stuff. They're not going to touch anything. In the parlance, my French accent just came out. In the parlance, in cryptography, we say that this thing is a man in the middle. So they can see what's happening here, but they can't really change it. Or they can try and change it, but TLS is secure, so it should be fine. And, oh, nice. And then what they're going to do is that they're going to stamp everything that they see. So we basically call that the transcript. They're gonna sign or stamp or whatever the transcript. How can I? TEEs. And that includes the handshake, that includes queries that were made, that includes responses, and all of that is encrypted. So they can't really see it, they can't really do anything with it. What they just do is that they witness the exchange that happened and the communication that happened. Then they're gonna give that back to me, and what I'm gonna do is that I'm gonna prove. I'm gonna use a zkP. So 1, and this is the proxy approach, I guess. And then I'm gonna use a zero-knowledge proof to decrypt the ciphertext in the transcript and prove that my queries were well constructed, and in the answer, my credit score was there, or my credit score was higher than something, or whatever. So zkP of decryption of transcripts. And so that's when it sort of gets complicated. There's some issues with this approach, basically. As I said, the symmetric key, once you, how to explain that? Okay, there's a lot of issues with this approach, and you can say it's fine or it's not fine. But some of the stuff is that, okay, the most obvious issue with that actually is that if I'm there, but I'm actually man in the middling, the man in the middle guy, so I'm here, right? So I can sort of inject my own ciphertext here, and we're back at the first stage, and we're back with the original issue we had. So that's one annoying thing. The other thing is that the proxy guy might actually be colluding with me. So they might sign stuff, but since they're trying to help me, they'll sign my fake transcript instead. And so that also has, that's also an issue. And maybe I'll talk about that next, before I talk about more crypto stuff. Okay, so this proxy guy, I'm gonna call that the notary, because they're sort of notarizing what they're saying. So far, they've notarized the transcript, the internet exchange. Notary. But I said that, I said that they might be colluding, so we don't necessarily want to trust one notary. If they're the one trying to verify something from me, then it's fine. They have no reason to cheat. But if we want to post that thing on chain, we can't really trust one person. And so at this point, we're back into the model I was talking about before with the public oracles. And basically, we have a committee of notaries, and we're trying to decentralize that trust. And so what I will do is that I will do that protocol with many notaries. And you have some economic security, and you're thinking that we should, if all of them have the same results, then we should be good, and these kind of things. Or we can take the average of all the results, or stuff like that. And what's interesting is that this might also sort of, fix the attack where I'm man in the middling the notary itself, because if I'm doing the protocol many, many times with many notaries in parallel, then it's harder for me to man in the middle each of them. So that's sort of one thing that all of these protocols have to solve is how can you have this sort of this set of notaries, this network of notaries, and how do we incentivize them not to cheat, how we detect when people cheat and these kind of things. I guess Hirsch here can tell you more about these kind of things and how to solve them. But yeah, that's the last time I'm going to talk about that. So yeah, any questions so far? Yeah.
Here's just going back to the proxy in the first place. So there's like a man in the middle. There's essentially like a TLS connection from like a client to the proxy and from the proxy to the server. And if the proxy can therefore like it decrypts and re-encrypts, how is that?
They don't. So the proxy here doesn't decrypt and re-encrypt. They're really just a pure man in the middle, like a dumb man in the middle. They just see ciphertext, like encrypted content, and they just forward it.
But
right?
if they're doing the handshake with the server, then they have the keys, so they technically could decrypt and re-encrypt.
No, because the handshake are also messages from me that they're just forwarding to the server. So you can think of them as just a node on the, you're already, when you talk to bank.com, you're already talking to a bunch of nodes or middle boxes on the network, right?
So they're facilitating the handshake, they're not actually doing it with the client and the server.
They're not facilitating the handshake. They're just like a dumb node in the network. They're seeing things, passing through them, and they're not touching things. Does that make sense from that? Yeah. And from maybe important to say that as well, from bank.com's perspective, they don't know that they're talking to me or to a proxy. They don't care, right? It's the same thing. Any other questions?
Is there any benefit by just having one proxy? Like if you're not using the network many, if you just have one between you and the bank, is there any benefit to the user?
Oh, if you only have one proxy, well, it's easier because like web applications they might return different things every time. So you're dealing with like potentially different results that all have the result that you want. You have to do many queries in parallel, but you might have to do many zero-knowledge proofs at some point, or like aggregate the result of these zero-knowledge proofs. So it is annoying, I would imagine. I haven't engineered that kind of protocol myself, but I would imagine that it's kind of painful. And if you can avoid it, then you should have only one. But it's not super secure, right?
Is it the same level of security as talking to the bank, or just the bank directly, or?
So from the user perspective, it's as secure as like that man. If TLS is secure, then that man in the middle cannot do anything. But here we're talking about moving that sort of data on chain, or moving like a statement on that data on chain. And so for that to be secure, we don't want to rely on only one proxy, because of what I talked. Like they could be colluding with you. Does that answer your question? Or?
Yeah. So like, just from the user's perspective, if they only have the option to like, if there's a proxy pool that only has one proxy in it, that was gonna help like be the man in the middle for them talking to the bank. It's better for them to just talk to the bank directly. If they only get the benefit if there's like a network of them.
Yeah. Basically, if you talk to the bank directly, then it doesn't work, right? You cannot prove anything to anyone, because the bank is not signing anything. So the only reason why you use that proxy is to really be able to have some sort of notary.
Or like show to a third party, because you're signing it to the bank, right? Like,
Yeah, it is a third party. It is sort of a trusted third party in a way, right? Actually, when you use a single proxy, you assume that it's the trusted third party. Does that make sense? Yeah. Yeah. And again, if the proxy is the person you're trying to convince, then they're a trusted party by design. They're So you don't need more proxies. Yeah.
In this world, can the bank and the proxy collude, or can only the client and the proxy collude?
Oh yeah. So the bank, we also assume that the bank is like not gonna emit wrongful data and is doing the right thing, right? Which is also another, it's a trust assumption. You're also trusting the certificate authorities and these kind of things. Yeah. Cool. Oh, yeah?
Why don't the bank just sign? So why don't
Oh, so the bank could sign in theory. they could have an API that they could use to sign, or they could use one of these extensions that I talked about that I don't think anybody uses. And basically, it's a matter of maybe they are too lazy to implement this API to provide these signatures, or they don't want. So like sometimes they don't want people to be able to access that data, or maybe they have a paid API. Like there's many reasons, but basically as the user, you just know that you don't have access to that. For whatever reason, the bank hasn't done that, is not allowing that to be done easily, and so you don't have a choice but to use these kind of protocols.
And if they do that, that would be the most secure.
Yeah, basically, the best thing you can do if you want your data to be on chain is to provide like an API, a stable API that you sign and so on. Yeah. So yeah, this thing is really interesting when you're not controlling the server, right? Cool. So this is the part that's kind of hard to explain because there's so many different design decisions in the space. But basically, the way I understand it is that the notary here has different degrees of notarization. Here, this is the simplest degree of notarization. They just looked at the traffic and they stamped it. Deco has this higher degree of notarization where they basically, how do I explain that? They will basically do an MPC with me, I'm the user, and they will do an MPC with me so that I don't control the key in the handshake with the server. So let's remove the proxy. Now there is no more proxy. Whoop. Yeah, how do I do that? So bank.com is here now. These three-party handshake are kind of hard to diagram. Also, three-party handshake is not a great name because there was an attack called three-party handshake or something like that. But the notary is going to sit here on the outside. They're going to talk to me, and they're going to do an MPC, so multi-party computation, so that the key that we're using here, or like somewhere here actually, there's depending on the protocol, on the version of TLS, the key that we're using is not controlled by us or by me. So, do I need to explain key exchanges? Maybe I should, maybe I... Okay, I'm not going to explain. You want me to explain key exchange? As a recap, okay, as a very fast recap, my key is this thing here. This is the server key. And to do a key exchange, so mine, server, I'm sending this as public key, the server is sending this as public key, and to do a key exchange, we do, the server will do B times A, and I will do A times, I will do B times A, the server will do A times B, which is GAB. If that doesn't make sense, don't sweat it too much. But what I want to show is that my private key here, when I do this MPC with the notary, is actually 2 shares, split in 2 shares. And I keep one of the share, and the notary keeps the other share. Okay? So that's really what I want to convey. You don't need to understand that. But my private key is split in 2 shares. I don't have access to it. The notary doesn't have access to it. If the notary had access to it, that would be really bad, because they could decrypt the session. And so now, whenever I send a request to bank.com, I'm going to have to do an MPC with the notary to encrypt my query, because I don't have access to these things, right? And whenever I receive an answer, I'm going to also have to do an MPC to decrypt, or the notary, if this is the notary share, the notary will send that to me. And this is kind of complicated. They have to make sure that there are some attacks. They cannot send that to me before I commit to the ciphertext, because again, if I learn the symmetric keys, I can lie about the ciphertext. So I need to send the ciphertext, the encrypted data, to the the notary, and then they release their share, and then I can decrypt and prove things. Does that make any sense? It's starting to get fuzzy, no? Okay, I want to rephrase that. So the notary has, the first notary was doing something very simple, right? It was just stamping encrypted data, was not doing anything. The second notary here has a higher degree of notarization because they're doing this computation with you to ensure that the keys are computed correctly and that you're doing a normal key derivation, that you ended up with the correct symmetric keys. And so you can think of it as a higher degree of notarization. They've done more work. At the end, their signature will be over something that's maybe more important in a way. Yeah, did you raise your hand there? Or?
Yeah, I guess in the case of the notary, it's just like a dumb note signing things. Like what actual verification are you getting if they're not verifying anything that's been changed or tampered with? And then the second case of doing the MPC with the notary, they're able to see that you didn't do anything weird with your keys, but what guarantees on the data tampering or whatever does that actually get you? So I guess in both cases, what is working with the dumb notary or the second order higher up notary actually get you in terms of data assurance?
So here, at this point, we haven't replaced too much of the protocol with an MPC, or we haven't added too many MPCs. The thing here is that since the notary is not a proxy anymore, they can't really ensure that the data or the ciphertext are legit. And so they have to do this key exchange with you, otherwise you might lie. So I would argue maybe they're sort of equivalent at this point. Although they do prevent against the man-in-the-middle attack that I've talked about earlier. And so they're somewhat equivalent, but there are some attacks that might work against one that doesn't work against the other. And yeah, I think we're talking about that also. You also can think of a world where these proxies might get banned by some servers. And so if you're letting the users do the queries to the websites themselves, they might not get censored or banned or blocked or these kind of things. So it's a trade-off space. There's different things that you're getting. But in terms of pure security in a simplistic model, where you think there's not going to be any man in the middle, then this is somewhat similar. Yeah.
Sort of like multi-sig versus MPC.
Why multi-sig?
Like in an analogous way, multi-sig would be so in the first protocol would be multiple notaries. So think of that as sort of a multi-sig.
So we still need multiple notaries.
Also an MPC.
Yeah, because here as well, the notary could be colluding with you.
Yeah.
Right? And so they could still lie, or the notary could be you also, and you could do that. So it doesn't change that.
No, yeah, I just said from a trade-off perspective, it's kind of similar to a lot of the trade-offs we would see in different blockchain or security protocols that opt to use multi-sigs versus an MPC network. You verify less signatures, compared to you verify one signature, but then you lose the overhead of doing key exchange and DKG or whatnot.
So,
I don't, yeah.
In the proxy architecture, if you assume that proxy notary is honest, you can still fake a proof by manually milling that proxy. But in the MPC architecture, because no one outside the server knows the symmetric key, if the MPC node is honest, then you can trust the proof. It's a big difference between the two.
Yeah, I don't. Yeah, I would say no, but maybe I didn't get it. Okay. But immediately, I don't think these are analogous. Yeah. Did someone raise their hand? Oh, yeah.
So just to clarify, with the initial framework, there's there's two issues. There's collusion and there's the man in the middle. Collusion is solved with multiple proxies or notaries.
Right.
The man in the middle is eventually solved with the MPC route, but you need both. So how do you have multiple notaries in this MPC context?
So the same way where you have multiple notaries in the proxy setting, you will just, as a user, try to do these queries in parallel and try to talk to many notaries and end up with the same kind of a...
So when you split the private key, the client keeps its half and then it gives that same other half to all of the different notaries and performs that kind of same...
Oh, no, it's not a... So multi-party computations are kind of a slow primitive. And so instead of doing a multi-party computation with many notaries, you're actually going to do two-party computations many times, right? Maybe in the future we get better schemes and we can do an actual one multi-party computation with many people, but...
In reality, is this MPC fast enough to not use any timeouts on the server because the server might start the TLS and then
Right. Yeah, that's a really good question. So, yeah, just to repeat, MPC takes time. You're communicating over the network to someone, so you might time out with the server during that time. I don't know, does that happen often, or?
It depends on the construction you use. With other techniques you have on your list, you can make it fast enough where it shouldn't be an issue.
Okay.
Do you know if there is any a standard timeout on TLS that's recommended or not?
The default is 30 seconds. Google's at 8. Yeah.
All right, default 30 seconds, Google 8. Yeah, I would guess it depends on the libraries you're using also.
So the man in the middle attack is essentially somebody impersonating Gate.com, right?
Yes, right.
So why does the MPC framework solve that?
So they solved that because let's put a man in the middle here. Basically, that key exchange part here, you won't be able to fake it because you need to present a certificate, right? So the keys are going to be legit at this point. And if you learn the symmetric keys, you can man in the middle that application data being sent and received as well. But at this point, when you enter the end of the handshake and you're actually making queries and receiving responses, you don't know the symmetric keys because they're shared. So you could try to still man in the middle of that, but since you don't know the symmetric keys, you're just going to produce garbage impersonating the server. There's basically no way you can construct correct ciphertexts. And so in this model, that's why you need to send the ciphertext first to commit to them, to the notary, and then they'll send you the share. It's very important that you do it in that order, otherwise you could do some pretty bad things.
In simplicity, does the notary ever get the plain text of the headers I'm trying to send to the plaintiff?
So it depends, I guess. What the notary could do is just stamp on stuff, and so then you can just prove that everything's correct, that you're talking to the right person, and these kind of things. Yeah, I guess it would depend on what you're trying to achieve, and yeah, I don't have a better answer. Maybe I should make a list of all the stuff that's really going on. But there's handshake. So you're doing that either normally through a proxy or you're doing an MPC to do that. Again, when we do the MPC, the server doesn't realize it, right? To them, they're only talking to one person. There's the derivation of keys, of symmetric keys. That you can also do in MPC, or you don't need to do it, or you can prove it in zk. Then you have the encryption of queries. If you control the symmetric key, then you can do it by yourself, or you can prove that you did it correctly with the right request or something like that. Or in the MPC mode, then you have to collaborate with the notary to encrypt the queries. Then there's the decryption of queries, of responses, sorry. So that, by the way, that's when it's getting complicated. Everybody's doing something different here. And depending on how you do things, you have to make sure you're secure. But decryption of requests, again, if you're the MPC thing, you have to do it collaboratively, or you have to receive the share and then you can do it. If you're in the proxy setting, you can do it yourself and you can do a zkP to prove that you did it yourself. And then there's like proof of statements. And the proof of statement is like, it's basically what you want to bring on chain. It's like, I queried my bank, and in the response, on the path was like credit score, bank.com/credit score, something like that. And the response, my credit score was 800. That statement, you can prove yourself in a zero-knowledge proof, or you can try to do, you can do it using an MPC, basically. And then the notary can sign the result. So you basically convince the notary of that using an MPC instead of locally doing a zero-knowledge proof, and they sign the results. What's interesting is that at the end, they just provide you with a signature, and you can bring that on chain instead of verifying a zero-knowledge proof, which might be expensive. And so that's, I guess, the highest degree of notarization that you can do, which is like, I've actually notarized a lot of things myself as the notary, not just the transcript, not just the handshake. I've also notarized the fact that the query was well constructed, that the response had the right number, whatever. And so, yeah, does that make sense what I said? There's different things. You can do them as MPC. You can prove them locally. Yeah, you sort of have the choice in that design space. Maybe one thing I can mention is that a lot of these MPCs, so for example, if you want to prove to the notary that and it's interesting because you're already trusting the notary to like sign something, right? Even in the simplest notarization, they're still signing the transcript. So you're already trusting a signature from the notary. So you could be like, okay, let's just go all the way. We're already trusting the notary to sign something. So let's not produce a zero-knowledge proof at the end. Let's just prove it to the notary and they'll sign it. And maybe that's enough. And so when you do that, these MPCs that you're doing with the notary are basically interactive zero-knowledge proofs. So that might be interesting to you. There's a bunch of schemes called Volley, and Quicksilver. And they're basically MPCs. And since in an MPC you can mask some of the inputs and stuff like that, you can think of them as interactive zero-knowledge proof.
Are those alternatives to Deco?
Basically, but so if you look at Deco now, like implemented by Chainlink, or what they're trying to do, I don't know if the project is still alive, by the way. No, I believe they're using Volley and Quicksilver and these kind of things. So there's really like Deco the paper, and then Deco like the project, and then there's other. So that's kind of hard to. It's kind of hard to trace that map, or to even answer that question, I guess. Maybe I can mention one last thing, but any questions before I mention the last thing? So I guess. Yeah, I've talked about TEEs. I've talked about doing stuff with zero-knowledge proof. I've talked about the MPC approach. And I've talked about interactive zero-knowledge proof or more MPC. I think it's interesting to note that there's also the FHE approach. So in the FHE approach, it's like, okay, we don't want the client to create a proof, or we don't want to do an MPC. We will have to do some of them, but we want to reduce the amount of them that we're doing. So let's just do the computation ourselves. And that's when the notary can just do the computation by themselves using FHE. So yeah, zero-knowledge proof is like the client can prove locally something. MPC is like we're both going to do it. FHE is like the notary is doing the computation. That's how you can see the space. Yeah, I don't know if I can do a table. Maybe that could be useful to recap. But notary, and that's me. And MPC is sort of in between. zk is only me, and FHE is only the notary. Or you could have an FHE network and the notary is also talking to someone else. But for the sake of simplicity, you can imagine that table. So yeah, that increased the design space even more. Cool. So I think that's pretty much all that I can say at this point. Maybe I can finish with some closing words. But yeah, any questions? And right, then I'll say my final words will be that I'm always trying to think of where zk can be useful. And one of the things I've realized over time is that zk is very useful when you're verifying signatures in zk. And so I see zkTLS as sort of an instance of that. Like you want to verify a signature in zk, but bank.com is not producing that signature for you. So we're going to produce that signature using a notary or several notaries. But at the end of the day, from the zk perspective, you're still verifying a signature and then proving some stuff on what was signed. It's just that the signature comes from a notary / notaries instead of bank.com. Yeah?
What are some reasons why bank.com wouldn't be incentivized to just like do all the signatures, like provide all the signatures themselves?
Yeah, so reason why bank.com wouldn't have like a sign API or something like that, like it depends. Maybe their engineers don't have the time to do it. Maybe they don't want you to have access to that feature. Maybe they have an API like that, but it's only for other banks. So it could be many reasons. Yeah.
Meta, for example, is super restrictive over their data in API, so they wouldn't just share data arbitrarily with you.
And maybe I can add also that back in the days, I'm not that old, but back in the days, like nobody would use TLS, right? So the way you would do APIs was to just crawl the web and parse a bunch of HTML. And of course that doesn't work well, but that's what we used to do. But it wouldn't work well with blockchain. But yeah, anyway, yeah, this is zkTLS. Hopefully that made sense. Cool. That's it? Yeah?
Yeah, I mean,
Eat some pudding.